Electromagnetism got you puzzled? You're not alone. Many students find this topic challenging, but with a bit of guidance, it can become much clearer. Let's dive into the fascinating world of electromagnetism and break it down step by step. Electromagnetism is a branch of physics that deals with the study of electric and magnetic fields and their interactions. It is a fundamental aspect of our understanding of the physical world and has numerous applications in technology and everyday life. Let's break it down in a flash. First up, electrostatics. This is the study of electric charges at rest. It deals with the forces, fields, and potentials associated with static charges. Electrostatics is crucial for understanding how charges interact when they are not in motion. The principles of electrostatics are applied in various fields, including electronics, chemistry, and even biology. Coulomb's law is fundamental here. It tells us that the force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. This means that as the distance between charges increases, the force decreases rapidly. Coulomb's law is essential for calculating the forces between charged particles and understanding the behavior of electric fields. Next, let's talk about the electric field. An electric field is defined as the force per unit charge. Imagine placing a small positive test charge in the vicinity of other charges. The electric field is the force that this test charge would experience. The direction of the field is the direction of the force on a positive test charge. Electric fields are visualized using field lines, which show the direction and strength of the field at different points in space. Then we have electric potential. This is the work done to move a charge from one point to another in an electric field. It's a measure of the potential energy per unit charge at a point in space. Think of it as the electric height that a charge is lifted to. Electric potential is a scalar quantity, meaning it has magnitude but no direction. It is often measured in volts and is a key concept in understanding electric circuits and energy transfer. Gauss's law is another cornerstone of electrostatics. It states that the electric flux through a closed surface is proportional to the enclosed charge. This law is particularly useful for calculating electric fields when dealing with symmetrical charge distributions. Gauss's law simplifies the process of finding electric fields in complex situations and is a powerful tool in theoretical and applied physics. Now let's move on to magnetostatics. A magnetic field is a vector field that surrounds magnetic materials and moving charges. Unlike electric fields, which originate from charges, magnetic fields are produced by moving charges or intrinsic magnetic moments of elementary particles. Magnetic fields play a crucial role in many natural phenomena and technological applications, such as electric motors, generators, and magnetic storage devices. The Biot-Savart law and Ampere's law are crucial here. The Biot-Savart law describes how currents generate magnetic fields, while Ampere's law relates the integrated magnetic field around a closed loop to the electric current passing through the loop. These laws help us understand the magnetic effects of currents. The Biot-Savart law is particularly useful for calculating the magnetic field produced by a current-carrying wire, while Ampere's law is essential for understanding the relationship between current and magnetic fields in more complex geometries. Onto electromagnetic induction. Faraday's law tells us that a changing magnetic flux induces an electromotive force, EMF. This is the principle behind transformers and electric generators. Lenz's law complements this by stating that the induced current will flow in a direction that opposes the change in magnetic flux, ensuring the conservation of energy. Electromagnetic induction is a fundamental concept in the generation and transmission of electrical energy and is the basis for many modern technologies. Maxwell's equations are the grand unifiers of electromagnetism. They combine all the previous laws into a comprehensive framework that predicts the existence of electromagnetic waves. These waves travel at the speed of light and include visible light, radio waves, X-rays and more. Maxwell's work showed that light itself is an electromagnetic wave. Maxwell's equations are a set of 4 equations that describe how electric and magnetic fields interact and propagate through space. They are fundamental to our understanding of electromagnetism and have far-reaching implications in both theoretical and applied physics. Lastly, the pointing vector represents the energy flow in an electromagnetic field. It points in the direction that energy is moving, and its magnitude is proportional to the rate of energy transfer per unit area. This concept is essential for understanding how energy is transmitted through electromagnetic waves. The pointing vector is a key concept in the study of electromagnetic radiation and energy transfer in various physical systems. Master these concepts and you're well on your way to conquering electromagnetism. With a solid understanding of these principles, you'll be able to tackle more complex problems and appreciate the beauty of how electric and magnetic fields interact. Keep studying, and soon, electromagnetism will be second nature to you. Remember, electromagnetism is a vast and fascinating field with many layers of complexity. As you delve deeper into the subject, you'll discover new insights and applications that will enhance your understanding of the physical world. So, keep exploring, stay curious, and enjoy the journey of learning electromagnetism.